Hi everyone, in this video we will discuss about the ARM processor system on chip. Let's get started. The ARM processor system on chip, SoC, is a fascinating topic within the realm of computer architecture, especially in the context of electronic engineering. Let's dive into it. Imagine you have a complex system, like a smartphone or a tablet, and you need a powerful yet energy-efficient processor to run various tasks efficiently. This is where ARM SoCs come into play. ARM, which stands for Advanced RISC Machine, designs the architecture for processors used in many devices, ranging from smartphones to supercomputers. An ARM SoC integrates multiple components onto a single chip. These components typically include the CPU, Central Processing Unit, GPU, Graphics Processing Unit, memory controllers, I/O interfaces, and sometimes even specialized accelerators for tasks like machine learning or image processing. The heart of an ARM SoC is its CPU. ARM processors are known for their reduced instruction set computing, RISC, architecture, which prioritizes simplicity and efficiency in instruction execution. This design philosophy allows ARM CPUs to deliver high performance while consuming minimal power, making them ideal for mobile devices and other battery-powered applications. One key aspect of ARM SoCs is their scalability. ARM offers a wide range of CPU cores, from simple microcontrollers to powerful multi-core processors. This scalability allows manufacturers to choose the appropriate CPU core for their specific application, whether it's a low-power wearable device or a high-performance server. Another important feature of ARM SoCs is their modularity. Manufacturers can customize ARM-based chips by integrating different components according to their requirements. For example, a smartphone SoC might include a CPU, GPU, modem, and image signal processor, while a microcontroller SoC might include just the CPU and memory controllers. ARM SoCs also excel in terms of power efficiency. Thanks to their RISC architecture and advanced power management techniques, ARM processors can deliver excellent performance per watt, making them well-suited for battery-powered devices where energy efficiency is critical. In addition to their energy efficiency, ARM SoCs offer excellent performance. ARM processors are widely used in smartphones, tablets, and other mobile devices, where they deliver smooth user experiences and handle demanding tasks like gaming and multimedia playback with ease. Furthermore, ARM SoCs are highly versatile. They are not only used in consumer electronics but also in automotive systems, industrial equipment, IoT devices, and more. Their flexibility and scalability make them suitable for a wide range of applications. In summary, ARM processor system on chips are integral to modern computing devices, offering a powerful combination of performance, energy efficiency, scalability, and versatility. As an electronic engineer, understanding the architecture and design principles behind ARM SoCs is essential for developing innovative and efficient solutions for a variety of applications. First, we will talk about the incredible shrinking CPU. The evolution of computing technology has been remarkable. In the early days, like during the era of the first-generation computers, the computing power we take for granted today was inconceivable. Back then, entire rooms were dedicated to housing, powering, and cooling the massive number of vacuum tubes required for a single CPU. These vacuum tubes were the fundamental building blocks of early electronic computers. They were large, fragile, and consumed a significant amount of power. Moreover, they generated a considerable amount of heat, necessitating extensive cooling systems to prevent overheating and ensure stable operation. These specially engineered buildings, often referred to as computer labs or computer rooms, were equipped with elaborate cooling systems, including air conditioning and ventilation, to maintain a suitable operating temperature for the delicate vacuum tubes. The power requirements for these early computers were also substantial, often requiring dedicated electrical substations to provide the necessary electricity. Despite their size, complexity, and power consumption, these first-generation computers represented groundbreaking advancements in technology. They laid the foundation for the digital revolution that would follow, paving the way for the development of more compact, efficient, and powerful computing devices in the years to come. the transition from these room-sized behemoths to the compact and energy-efficient processors we have today, like ARM-based SoCs, demonstrates the incredible progress that has been made in the field of computer architecture and electronic engineering. It's a testament to human ingenuity and innovation, driving us towards a future where computing power is more accessible, affordable, and ubiquitous than ever before. Now, let's delve into the advancements seen in the second generation of computers, which marked a significant leap forward from the massive, room-sized machines of the first generation. During the second generation of computers, which emerged in the late 1950s and lasted through the late 1960s, we witnessed remarkable advancements in technology that allowed for more compact and efficient computing systems. One notable example is the PDP-8 series of mini-computers developed by Digital Equipment Corporation, DEC. These machines were groundbreaking for their time because they were significantly smaller and more affordable than the mainframe computers that preceded them. The original PDP-8 machines were indeed much smaller than the room-sized behemoths of the first generation. They typically occupied only 3 or 4 cabinets, each about the size of a refrigerator. This reduction in size was made possible by advancements in printed circuit technology, which allowed for the integration of electronic components onto compact circuit boards. The PDP-8 series played a crucial role in democratizing computing by making powerful computing capabilities accessible to a broader range of organizations and institutions. They were used in a variety of applications, including scientific research, industrial control systems, and early interactive computing experiments. One key innovation of the PDP-8 series was its use of a simplified instruction set architecture, ISA, which made programming and operating the machines more accessible to users. This contributed to their widespread adoption and popularity in academic and research settings. The transition from room-sized mainframes to refrigerator-sized mini-computers represented a significant milestone in the history of computing. It demonstrated that computing power could be packaged in a more compact and affordable form factor, paving the way for further advancements in the decades to come. In the third generation of computers, which began in the late 1960s and continued into the 1970s, the integration of transistors into integrated circuits, ICs, revolutionized computing technology. This era marked a significant shift towards smaller, more powerful, and more affordable computing systems. One of the key advancements of the third generation was the development of integrated circuits, which allowed for the integration of multiple transistors and other electronic components onto a single semiconductor chip. This miniaturization of components dramatically reduced the size and cost of electronic devices, including computers. With the advent of integrated circuits, the size of the central processing unit, CPU, itself shrank significantly. Instead of occupying multiple cabinets or even an entire room, the CPU could now fit on a single chip, often referred to as a microprocessor. These early microprocessors were indeed small enough to fit on a desktop and were only slightly larger than the first personal computers. One of the most iconic examples of a third-generation microprocessor is the Intel 4004, introduced in 1971. Developed by Intel Corporation, the 4004 was the world's first commercially available microprocessor. It contained 2,300 transistors and was capable of performing up to 60,000 operations per second. Despite its modest processing power by today's standards, the Intel 4004 represented a significant milestone in the evolution of computing technology. The introduction of microprocessors revolutionized the computer industry by enabling the development of smaller, more affordable, and more versatile computing devices. These devices paved the way for the emergence of the personal computer revolution in the late 1970s and early 1980s, as microprocessors. The third generation of computers also saw advancements in other areas, such as memory technology and input-output I/O devices. Integrated circuits made it possible to manufacture larger and faster memory chips, while improvements in I/O technology allowed for faster data transfer between computers and peripheral devices. Overall, the integration of transistors into integrated circuits during the third generation of computers marked a significant milestone in the history of computing technology. It laid the groundwork for the development of smaller, more powerful, and more affordable computing devices, paving the way for the digital revolution that would follow. They highlighted a crucial period in the history of microprocessors, where Motorola and Intel emerged as dominant players with their respective architectures, the 68000 and the x86 series, notably the 8086 and its variants. The Intel 8086, introduced in 1978, was a pivotal microprocessor in the history of personal computing. Its architecture laid the foundation for the x86 family of processors, which would become the standard for IBM-compatible personal computers. The IBM PC, powered by the 8088 variant of the 8086, propelled personal computing into the business world, setting the stage for the widespread adoption of desktop computers. Meanwhile, the Motorola 68000 series of microprocessors also made significant contributions to computing technology. The 68000, with its powerful instruction set and versatile architecture, powered a range of graphical user interface (GUI) computers, including workstations from Sun Microsystems and Apollo Computer, as well as the Apple Lisa and Macintosh. However, despite its capabilities, the 68000 architecture faced challenges in competing with Intel's x86 architecture, particularly in the rapidly growing PC market. Intel's aggressive marketing strategies and strong partnerships with major PC manufacturers contributed to the dominance of the x86 architecture in the personal computing industry. By the mid-1990s, the x86 architecture had become the de facto standard for personal computers, while the use of the 68000 architecture declined. Motorola struggled to keep up with Intel's pace of innovation and market dominance, leading to the gradual obsolescence of the 68000 series in mainstream computing. Nonetheless, the legacy of the 68000 architecture lives on in various embedded systems, industrial applications, and legacy computing platforms. Its influence can still be seen in modern microprocessor designs and instruction set architectures. Indeed, the shift to Intel processors in Apple's Macintosh line in 2006 marked a significant turning point in the personal computing industry. Intel's dominance in the market continued to solidify over the years, with their processors becoming the standard choice for a wide range of computing devices, from desktops and laptops to servers and supercomputers. The exponential growth in transistor count within Intel's processors illustrates the remarkable advancements in semiconductor technology over the years. By 2016, Intel's Haswell E CPUs boasted an astonishing 2.6 billion transistors, demonstrating the increasing complexity and sophistication of modern microprocessor designs. These high transistor counts allowed for greater processing power, improved energy efficiency, and enhanced feature sets, enabling a wide range of applications across various computing platforms. In the realm of server computing, Intel's Xeon processors, including the Knights Corner Xeon Phi supercomputer component, pushed the boundaries even further. With a staggering 7 billion transistors, the Xeon Phi represented the pinnacle of Intel's server processor lineup, delivering unparalleled performance for high-performance computing, HPC, and scientific applications. Intel's dominance in personal computing and server markets can be attributed to their relentless pursuit of innovation and their ability to push the limits of semiconductor technology. Their processors have become synonymous with performance, reliability, and scalability, making them the go-to choice for many organizations and individuals worldwide. Looking ahead, the continued evolution of Intel's processor technology promises even greater advancements in computing performance, efficiency, and capabilities, driving innovation across a wide range of industries and applications. Logic gate. Logic gates are the fundamental building blocks of digital computer circuits, enabling them to perform various logical and arithmetic operations. There are four basic types of logic gates. 1. NOT gate, also known as an inverter. The NOT gate accepts a single input and produces the logical opposite as output. In other words, if the input is 0, the output is 1, and vice versa. AND gate. The AND gate accepts two or more inputs and produces a 1 output only if all of its inputs are 1. Otherwise, it produces a 0 output. 2. OR gate. The OR gate accepts two or more inputs and produces a 1 output if any of its inputs are 1. It produces a 0 output only if all of its inputs are 0. 3. XOR gate. The XOR, exclusive OR, gate accepts two inputs and produces a 1 output if exactly one of its inputs is 1. If both inputs are the same, either both 0 or both 1, it produces a 0 output. These basic logic gates can be combined in various ways to perform more complex logical and arithmetic operations. For example, combinations of AND, OR, and NOT gates can be used to implement addition, subtraction, multiplication, and other mathematical operations in digital circuits. Furthermore, modern digital circuits often use more advanced logic gates and components, such as flip-flops, multiplexers, and programmable logic devices, to implement complex functions and perform tasks efficiently. Overall, logic gates play a crucial role in the operation of digital computers, allowing them to process and manipulate binary data according to logical rules and algorithms. Next, we will discuss about CMOS. CMOS, complementary metal oxide semiconductor, technology lies at the heart of modern digital integrated circuits. These circuits, which form the basis of most digital electronic devices, are constructed using a combination of NMOS and PMOS transistors. In a CMOS circuit, NMOS and PMOS transistors are used in complementary pairs to implement logic functions. Each transistor type plays a specific role in the operation of the circuit. 1. NMOS transistors. These transistors are typically used to implement the low side of a logic gate. In other words, they conduct and the input signal is high, logic 1. When the input signal is low, logic 0, the NMOS transistor is turned off, effectively representing a logical 0 output. 2. PMOS transistors. Conversely, PMOS transistors are used to implement the high side of a logic gate. They conduct when the input signal is low, logic 0. When the input signal is high, logic 1, the PMOS transistor is turned off, resulting in a logical 1 output. By combining NMOS and PMOS transistors in complementary pairs, CMOS circuits can implement a wide range of complex logic functions efficiently and reliably. These functions can include AND, OR, NOT, XOR, and many others, as well as more complex functions with multiple inputs. The use of CMOS technology offers several advantages, including low power consumption, high noise immunity, and compatibility with modern semiconductor manufacturing processes. These characteristics make CMOS technology well suited for a wide range of applications, from microprocessors and memory chips to digital signal processors and system-on-chip (SoC) devices. In summary, while modern CMOS cell libraries may contain hundreds of cells computing complex functions with multiple inputs at their core, these functions are constructed using the basic principles of NMOS and PMOS transistors working in complementary pairs to implement logic operations. This figure discusses about a CMOS NOT gate is a fundamental logic gate that produces the complement of its input signal. It consists of both NMOS and PMOS transistors arranged in a specific configuration. Let's describe a simplified schematic diagram of a CMOS NOT gate. 1 input signal, A. The input signal to the NOT gate, denoted as A, 2 NMOS transistor, N1 an NMOS transistor connected between the input signal, A, and the output node. The source of the NMOS transistor is connected to the ground, 0V, and its drain is connected to the output node. The gate of the NMOS transistor is connected to the input signal, 3 PMOS transistor, P1 a PMOS transistor connected between the output node and the power supply voltage, V_DD. The source of the PMOS transistor is connected to the power supply voltage, V_DD, and its drain is connected to the output node. The gate of the PMOS transistor is also connected to the input signal, for output signal, Y. The output signal of the NOT gate, denoted as Y, is the complement of the input signal, A. It is the voltage at the output node, which changes based on the input signal and the operation of the transistors. When the input signal, A, is at logic 0, ground, the NMOS transistor, N1, is turned off, and the PMOS transistor, P1, is turned on. As a result, the output node is pulled up to the power supply voltage, V_DD, resulting in a logic 1 output signal, Y. Conversely, when the input signal, A, is at logic 1, V_DD, the NMOS transistor, N1, is turned on, and the PMOS transistor, P1, is turned off. This connects the output node to ground, resulting in a logic 0 output signal, Y. In summary, a CMOS NOT gate utilizes both NMOS and PMOS transistors to produce the complement of its input signal. When the input signal is low, the output is high, and vice versa, making it a fundamental building block in digital logic circuits.